Welcome to the Deep Dive, where we take the carefully curated stack of sources you share with us and distill them into the crucial nuggets of knowledge, insight, and, well, surprise.
And today, the subject is definitely full of surprises.
Right. Today, we are deep diving into the life and career of a true American groundbreaker, Dr. Ellen Ochoa.
Indeed.
Yeah.
When you step back and, look at Dr. Ochoa's trajectory, it is the perfect illustration of how mastery in one highly specific technical field, in her case, applied optics, can launch a career not just into space.
Which is amazing enough.
Right, but into the absolute highest levels of operational command and national science policy. It's quite a leap.
It's a massive leap. She is, of course, rightly famous for two historic milestones, being the first Latina to go to space and then later becoming the first Hispanic director of the legendary Johnson Space Center.
Mm-hmm.
But as you just noted, those titles, as incredible as they are, they only scratch the surface of her technical and administrative genius.
They really do.
Yeah.
Our source material on her is very comprehensive. It traces her journey all the way from a childhood in La Mesa, California.
Okay.
Through securing these advanced degrees from Stanford, becoming a patented inventor, completing 4 really rigorous space missions, and then ultimately ascending to top-tier NASA management.
So our mission today is pretty laser-focused. We need to understand the how and the why.
Yes.
What specific innovations did she actually create, and how did that highly technical, almost niche background, this ability to teach computers how to see, how did that make her the indispensable operational and strategic leader she became? We're really tracing the intellectual backbone of her success.
And that intellectual backbone is built on a very, very potent academic foundation. Here's an initial nugget that just establishes the rigor of her approach right from the start.
Let's hear.
She first earned a Bachelor of Science degree in physics from San Diego State University, graduating Phi Beta Kappa.
Which is phenomenal, of course.
Phenomenal. But she didn't stop there. She layered that foundational scientific knowledge with applied engineering, earning both her master's and her PhD in electrical engineering from Stanford.
That combination, pure physical theory married to cutting-edge electronic application, that's a profile for someone who doesn't just manage existing technology.
No, not at all.
That's someone who fundamentally invents new ways of solving problems, and that really feels like the starting point for our deep dive.
To really understand the climb, I think we have to contextualize her roots.
Mm-hmm.
Ellen Ochoa was born on May 10th, 1958 in Los Angeles, though she grew up primarily in La Mesa, California.
Okay.
She was the middle child of 5, and the sources really stressed that she was charting new academic territory for her family.
And that's a crucial detail, I think. It really humanizes the data. Neither of her parents held a college degree. Her paternal grandparents had emigrated from Sonora, Mexico, moving first to Arizona and then settling in California.
Exactly. So this was a family background rooted in hard work, absolutely, but not necessarily in higher education or, academic science.
Which makes her decision to pursue advanced physics and then engineering even more remarkable.
It does. She graduated from Grossmont High School in El Cajon in 1975. And this period, it was personally challenging for her. Her parents divorced while she was in high school.
Wow.
Yet she maintained her focus, and she headed to San Diego State University.
And, a lot of students enter college unsure of their path, right? Mm-hmm. They explore a bit. But it was at SDSU that she had this crucial realization that just drove the rest of her career.
What was that?
While pursuing that BS in physics, which she completed in 1980, she discovered that she didn't just love the abstract theory of physics and math, she loved the application. She loved engineering.
And that distinction is so key. Physics teaches you how the world works. Engineering teaches you how to build a world that works better.
That's a great way to put it.
That realization, it just fueled her decision to pursue advanced degrees at Stanford, specifically shifting to electrical engineering. That gave her the technical toolkit to turn these theoretical principles into functioning, deployable systems.
So she got her MS in 1981 and then the PhD in 1985.
Correct.
But let's pause here. Let's move past the academic titles and get into the nuts and bolts of what she was actually building. This is where it gets really interesting. The power of applied optics.
Yes.
What exactly was she researching during this pivotal period at Stanford?
Well, optics, in her context, was far more esoteric than you might assume. We're not talking about, simple photography or designing a better camera lens.
Right.
Ochoa's core research focus was on developing optical systems designed for information processing.
Okay, to make that accessible for everyone listening, what was the practical goal? What does that mean?
Simply put, the goal was to help computers see and process visual information using light waves.
Light waves. not electronic signals.
Right. Using things like diffraction and interference to perform calculations physically with light, rather than relying solely on traditional electronic chips, which process data sequentially, one step at a time.
So she was researching a form of parallel visual processing way before that concept became mainstream in AI.
Exactly. This technology had the potential to vastly increase the speed and efficiency of analyzing complex visual data. It's a foundational concept.
That is genuinely fascinating. It means her expertise was fundamentally about automating complex visual decision-making. And that skill set is valuable. Well, everywhere.
It's valuable everywhere, which is why her research spanned multiple high-level institutions. She was not confined to one ivory tower.
This technical adaptability seems to be one of her hallmarks.
It really is. First, of course, she developed the theoretical framework during her doctoral work at Stanford. But second, she took those specialized skills directly to Sandia National Laboratories.
Sandia, that's a national security environment, right? Often associated with nuclear weapons research and very high-stakes engineering. Why was an optics expert like her needed there?
Her work at Sandia applied optics to highly sensitive research problems. I mean, when you are dealing with complex systems that must perform flawlessly, whether it's a weapons component or a critical sensor array, you need instant non-invasive quality control.
Okay, so you need to check for flaws without taking it apart.
Precisely. Her ability to use light to analyze systems was deemed absolutely critical for national security.
And then finally, she made the critical jump from Sandia to the NASA Ames Research Center, which that sets the stage for her entire astronaut career.
It really does. At Ames, she was leading a research group focused on optical systems, but now the application was explicitly tailored for automated space exploration.
She was a manager there?
She was the chief of the Intelligent Systems Technology branch. She was supervising 35 engineers and scientists. This was a substantial management role focused entirely on computational systems for aerospace.
So this shows a really clear pipeline. Her niche technical skill was so valuable that it just automatically propelled her into executive management positions even before she was selected for the astronaut corps. But let's solidify her status as a genuine inventor. I want to dig into the specifics of the 3 patents she holds.
Yes. The 3 patents are the definitive proof of her original contribution to machine vision. Let's break down the engineering problem each one solved, moving beyond just the formal titles.
Great. Let's start with patent number 1, the optical inspection system designed to detect defects in repeating patterns. What does that do?
This patent was critical for high-precision manufacturing and quality control. So think about a semiconductor chip or a printed circuit board.
Okay, things with tons of tiny identical lines on them.
Exactly. Microscopic repeating patterns. If just one line is infinitesimally thin, or if an impurity, a tiny particle of dust, maybe lands on the wafer, the entire component fails.
And a human eye could never spot that reliably.
Never. Her system used light interference patterns and diffraction to rapidly and automatically detect these tiny flaws at a speed and precision that human inspectors just could never match.
So it ensured reliability at the microscopic level. In a high-reliability industry like aerospace, where failure is not an option, that kind of automation is a necessity, not a luxury.
Absolutely. Which leads us directly to the second patent, an automated inspection system designed to analyze manufactured components for imperfections or defects. This one broadened the scope.
So it wasn't just about microchips anymore.
Correct. Now is about inspecting larger fabricated components.
Can you give us a real-world example of what that might be used for?
Sure. Imagine checking a critical weld joint on a pressurized fuel tank, or maybe the composite material on a spacecraft's heat shield.
Things you really need to be perfect.
Things that have to be perfect. Traditional methods might involve X-rays, which are slow, or manual inspection, which is fallible. Ochoa's optical system provided a non-contact, rapid way to scan the component's surface or even its internal structure for structural weakness, stress fractures, or inconsistent material density.
So this technology is foundational to ensuring every single piece of hardware launched into orbit meets space-grade reliability standards.
You got it.
That makes perfect sense. Now, the third patent seems to take a slightly different turn. It focuses more on recognition, a method and apparatus designed to recognize texture patterns from photos.
This is where we see the most direct link to exploration robotics. This patent goes beyond simple flaw detection and moves into automated environmental recognition and mapping.
So helping a robot understand what it's looking at.
Exactly.
Yep.
Consider the challenges facing an unmanned rover on Mars or the Moon. It can't rely on shadows or simple contrast to navigate. It needs to instantly determine in real time what it is driving on.
So the optical system has to make a crucial judgment call. Is this loose, fine-grained sand, what they call regolith, which is easy to get stuck in?
Right.
Or is this solid, stable bedrock that provides good traction? Or maybe is that a patch of frozen ice that it has to avoid?
Exactly. Ochoa's system analyzed the minute patterns or textures in the visual data captured by the camera, processed that pattern optically, and instantly categorized the surface material. This provided the foundational algorithms necessary to automate that crucial judgment call of safe pathing for space robotics.
Her technology was laying the groundwork for true autonomy in space exploration vehicles.
That's right.
This fundamentally changes the narrative of her career transition for me. It's not just about a smart engineer who decided to apply to be an astronaut.
No, it's much more strategic than that.
It's about NASA recognizing that her specific, highly technical invention, her unique ability to teach machines how to process visual data autonomously, was a necessary ingredient for the future of their automated and crewed missions.
They didn't just need a smart person. They needed that inventor with those 3 patents on the team.
It speaks volumes that by 1988, 2 years before her astronaut selection, she was already the chief of a major research project focused on intelligence systems for NASA. She was in high-level management before she ever put on a flight suit.
And that really sets up the next question, right? Given how complex and valuable her niche technical expertise was.
Yeah, why did NASA transition her into operational roles so quickly? Why move her out of the lab and into the flight deck? Wasn't there a risk of losing that incredible R&D expertise?
You know, what's so fascinating here is that NASA viewed her technical skills as assets for operations, not separate from them. They needed people who could truly understand the deep mechanics of the systems they were building, the software, the robotics, the hardware, especially as the complexity was about to explode with the upcoming International Space Station assembly.
So she wasn't just an operator, she was a super user.
The ultimate super user. She was chosen because she was uniquely qualified to both operate and troubleshoot the advanced systems she had, in a very real sense, helped conceptualize.
Okay, so let's unpack this monumental shift. From the Intelligence Systems Lab bench at Ames to the flight deck of the Space Shuttle, Ellen Ochoa was selected by NASA in January 1990. She was part of NASA Group 13, a class that carried the humorous nickname the Hairballs.
The Hairballs, yes. She officially became an astronaut in July 1991.
And instantly, her selection carried this immense historical significance. It marked a monumental moment for representation in spaceflight history.
Absolutely. She achieved groundbreaking status, becoming the first Latina to travel to space when she served on her first mission in 1993. This was a critical step in making the astronaut corps reflective of the nation it served.
But before she even took her first flight, her technical depth meant she wasn't just going through boilerplate training. She was immediately integrated into the core technical and operational framework of the astronaut office.
That is a critical point. Her early ground assignments, they included serving as the crew representative for some of the most complex, high-risk systems, flight software, computer hardware, and robotics.
She wasn't handed basic tasks. She was put in charge of the intellectual and technical interface between the crew, the people flying, and the engineering teams on the ground.
She spoke their language. She spoke the language of the hardware, understanding the algorithms and systems at a patent-level depth. That expertise was immediately leveraged.
She also served as assistant for Space Station to the chief of the astronaut office, which clearly demonstrates her leadership potential in managing the immense planning complexity surrounding the nascent International Space Station. But perhaps the most high-stakes ground role she held was serving as the lead Capcom, the spacecraft communicator, in mission control.
The Capcom is, I would argue, the most crucial role on the ground during a mission. They are the only people authorized to speak directly to the astronauts in orbit.
The one voice thing.
The one voice. And that job requires not only technical precision to translate engineering jargon and procedural changes into concise language, but also immense emotional calm under pressure. You have to synthesize data rapidly, make split-second decisions based on telemetry, and communicate those decisions clearly to the crew hundreds of miles above Earth.
Ochoa's background in precise information processing, her whole academic career, made her ideal for this role.
Absolutely. And then her operational career in space just cemented her status as a technical veteran. She completed 4 missions, logging nearly 1,000 hours in space.
1,000 hours. That's roughly 42 days worth of continuous time orbiting Earth. That's a massive portfolio of operational experience.
It is. Let's look at those missions because they really chart the arc of the space shuttle program. Her first, STS-56 in 1993, aboard Space Shuttle Discovery, that was her groundbreaking mission.
What was the goal of that flight?
It was a 9-day scientific mission focused primarily on studying the Earth's ozone layer and its relationship to the solar energy that drives our planet's systems. This scientific focus aligns perfectly with her original physics background.
It comes full circle. And of course, this is where we get that fantastic personal detail. She carried her classical flute with her into orbit, a physical representation of that balance between rigorous science and disciplined artistry.
A great story. And then on her second mission, STS-60 she immediately had her leadership status elevated. She served as payload commander.
So what does a payload commander do?
That meant she was taking charge of the entire suite of scientific experiments and specialized hardware the shuttle carried. She was overseeing their deployment, their operation, and all the data collection. Her technical management experience from NASA Ames was already paying huge dividends in orbit.
Now, her third and fourth missions, STS-96 and STS-110, these are truly foundational for the future of human spaceflight because they focus on the construction of the ISS.
That's right.
So let's start with the third one, STS-96, where she served as mission specialist and flight engineer. What made that flight so uniquely challenging?
Well, STS-96, which was in 1999, was highly significant because it was the first docking of a space shuttle with the newly launched International Space Station.
The very first one.
The very first. This was an unprecedented operation. The crew wasn't just docking a vehicle. They were delivering 4 tons of supplies, equipment, and performing really complex maneuvers to prepare the station for its first long-duration inhabitants.
And we circle right back to her patents here, don't we? Docking, especially first-time docking, it has to rely heavily on robotics, navigation systems, and real-time visual assessment.
You're exactly right. She was the one who held the deep technical expertise in those domains. The success of that docking, the precision required to maneuver a massive vehicle into a brand new space station. It relied directly on the kind of computational and robotics systems that Ochoa had spent her career developing and testing.
She was the ideal flight engineer for that kind of pioneering technical mission.
No question.
And her final flight, STS-110 in 2002, continued this critical work. Again, she served as mission specialist and flight engineer, but this time the mission was focused squarely on the ongoing assembly of the ISS structure itself.
This flight carried the S0 truss, a critical backbone element for the station. It was an intense, real-time construction mission in space, involving a spacewalk.
And her role.
She was responsible for operating the Canadarm, the shuttle's robotic manipulator system, which again, it just highlights the critical application of her early research into intelligent, automated visual systems. She was physically building the future of this space station with a robotic arm.
Amazing. Now, following her active flight career, we have a truly sobering but crucial detail that underscores the depth of her administrative role back on the ground.
Yes.
She was physically present in mission control during the devastating Space Shuttle Columbia disaster in February 2003.
This detail highlights the incredibly high-stakes environment in which she operated. Having served as a lead HAPSCOM and deputy chief of the astronaut office, she was a critical pillar of NASA's operational management. And the sources confirm she was among the very first personnel to receive the horrific news as the shuttle disintegrated upon re-entry.
I can only imagine the sheer gravity of being in that room at that moment, dealing with the loss of friends, of colleagues.
Her technical and administrative presence during the immediate aftermath was absolutely critical. She was instrumental in the investigation process, helping to analyze data, reconstruct events, and manage the painful, complex stand-down of the entire space shuttle program.
That experience, that crucible, it must have tested her not only for technical mastery, but for immense crisis management skills.
And the ability to maintain organizational integrity under the most tragic circumstances imaginable. These are the qualities that are essential for her next massive career shift, leading the entire center.
That's a powerful and necessary bridge. The intensity and leadership required in the immediate aftermath of Columbia showed she possessed the mettle required to steer the organization through its darkest hour and into the future.
The transition from active flight operations and crisis management to executive leadership was immediate and profound. After retiring from spacecraft operations in 2007, she seamlessly moved into the highest ranks of NASA management, leveraging all of that deep operational knowledge.
And she first served as deputy director of NASA's Johnson Space Center, JSC. For those who might be unfamiliar with the scale, JSC isn't just a building.
No.
It is the heart of human spaceflight. It's where astronauts are trained, it's where mission control operates, and it's where the planning for the entire crewed program, including Orion, the ISS, and future Artemis missions, is coordinated.
So serving as deputy director is essentially being the chief operating officer of human spaceflight.
Right. You're overseeing the entire astronaut office, aircraft operations, massive budgets. It's a huge job.
And this deputy role served as the proving ground for the pinnacle of her NASA career. On January 1st, 2013, she took over from Michael Coates and officially became the director of the Johnson Space Center.
And this achievement cemented two major historical milestones. She was the first Hispanic director of JSC, and she was only the second woman to ever hold that position.
It's the ultimate convergence. The physics student, the electrical engineer, the patented inventor, the for-flight astronaut, now commanding the entirety of the U.S. human spaceflight infrastructure.
What does that job even entail on a day-to-day basis? It seems monumental.
It is. Directing JSC is a monumental administrative undertaking. It involves managing thousands of employees, scientists, engineers, navigating complex political landscapes in Washington, D.C., and setting the strategic direction for missions that won't even launch for decades. Ochoa was responsible for everything from safety protocols to the development timeline for next-generation vehicles.
She proved that deep technical specialization translates directly into unparalleled administrative capability.
It really did.
But her influence quickly spread beyond the walls of NASA and into the strategic governance of American science itself. She demonstrated that a specialized technical background can be a launchpad for broader national policy.
That's the key takeaway here. She was named vice chair of the National Science Board, the NSB, for the 2018-2020 term.
And the NSB is the governing body of the National Science Foundation, which essentially guides U.S. fundamental research policy.
Right. I mean, think about that trajectory. From managing robotic arms in orbit, she shifted to shaping the nation's entire scientific and engineering agenda, guiding billions of dollars in research funding.
And she continues to contribute at the highest level of technical recognition today. She chairs the committee that evaluates nominations for the prestigious National Medal of Technology and Innovation.
So she is literally the gatekeeper for recognizing America's most significant technical breakthroughs.
And this brings us to a remarkable full-circle moment that connects her 1980s patents directly to the 2020s digital revolution. We have to note her very recent corporate appointment. In November 2024, she joined the board of NVIDIA.
This is such a fascinating development.
This appointment provides the perfect opportunity to validate our initial thesis. Optics leads to command. NVIDIA is the global leader in high-performance computing, particularly graphical processing units, GPUs, which are the backbone of modern AI and large-scale data visualization.
Right.
So why does a patented optics expert from the 80s belong on that board?
Because her foundational work on parallel visual information processing, teaching computers how to rapidly interpret images using light, is the conceptual ancestor of the massive computational challenges NVIDIA solves today.
So it's the same core problem, just at a vastly different scale.
Exactly. Her 3 patents weren't about traditional serial computing. They were about achieving speed and precision by leveraging the physics of light to process information simultaneously. That deep foundational understanding of automated machine vision and parallel processing is immensely valuable as companies like NVIDIA push the boundaries of AI, autonomous vehicles, and real-time data analysis.
It's proof that foundational knowledge is never obsolete. It simply finds new, more powerful applications. The underlying principles of her work are now defining the strategy of the world's most cutting-edge computing company.
And, let's take a moment here to return to that personal detail we love so much.
Yeah.
The classical flute.
Yes.
We know she's an accomplished classical musician who even took her instrument into space.
It's such a fantastic juxtaposition. The incredibly precise mathematical mind required for electrical engineering and aerospace systems, paired with the highly disciplined, emotive artistry required to master a musical instrument.
Does that suggest a balance between rigor and creativity that's essential for success in these high-stakes fields?
I think it has to.
I believe it does. Both engineering and classical music require meticulous attention to detail, endless practice, and the ability to execute complex sequences flawlessly under pressure.
Right. Whether you are running a docking procedure or performing a complex concerto, discipline and precision are paramount.
Exactly. The flute detail, it humanizes the data. It shows that behind the director and the astronaut is a complete multidimensional person whose passion for artistry likely fed her technical discipline.
So, Dr. Ochoa's decades of service and technical innovation have been recognized with an astonishing array of high honors and fellowships. It really validates the depth of her operational, technical, and administrative impact.
It really does. And we can group these honors by what they recognized. First, her operational skill was recognized throughout her time as an active astronaut. She received 4 spaceflight medals, one for each mission.
1983, 94, 99, and 2002.
Correct.
And then second, her leadership and administrative prowess were swiftly recognized. She earned the Outstanding Leadership Medal in 1995 and the Exceptional Service Medal in 1997.
And then the highest honor the agency gives, NASA's Distinguished Service Medal, was awarded to her in 2015, which recognizes the impact of her tenure as the JSC director.
Beyond NASA, her place in history is cemented in the Halls of Fame. She was inducted into the U.S. Astronaut Hall of Fame in 2017.
And the International Air and Space Hall of Fame in 2018. But if we connect this to the bigger picture of national recognition, a crowning achievement came just recently.
That would be the Presidential Medal of Freedom, which she received from President Joe Biden in 2024. That places her in the highest strata of American citizens recognized for exemplary deeds.
It's a monumental recognition of her contributions spanning technology, exploration, and administration.
And we also see her deep technical credibility reflected in her professional fellowships.
Yes, she is a fellow of the American Association for the Advancement of Science, the American Institute of Aeronautics and Astronautics, and crucially, the National Academy of Inventors, which ties right back to those 3 patents.
And she's also a fellow of Optica, which confirms that she remains recognized by her original specialized community. Still one of them.
Still one of them.
But perhaps the most powerful and tangible part of her legacy is in the realm of education. She has numerous schools named after her, creating these physical monuments that inspired the next generation of scientists and engineers.
It's an incredibly powerful form of institutional recognition. We're talking about multiple middle schools and elementary schools across the country, in Washington, California, Texas, Oklahoma, New Jersey, often with a dedicated STEM focus.
Like the Ellen Ochoa STEM Academy in Grand Prairie, Texas.
Exactly. Naming a school after a scientist and explorer sends a very clear message about what society values.
And there is a specific anecdote related to Ochoa Middle School in Pasco, Washington, that just perfectly connects her history to these students. The flag with the school's rocket logo was not merely honored.
No.
It flew with her.
That's right. That flag was aboard the Space Shuttle Atlantis during her 11-day mission to the ISS in April 2002. And she didn't just fly it and send it back. She personally returned it to the school when she visited as a special guest at the 2002 dedication.
Wow.
That artifact, which physically traveled into space, is now on permanent display at the school. It provides students with a concrete physical link to human exploration and technical achievement.
Finally, she's achieved that unique status reserved for true icons, inclusion in popular culture. In 2019, an animated version of Ochoa was featured in the children's television program Ready, Jet, Go.
Right. And perhaps the clearest signal of her becoming an enduring icon for the next generation of girls in STEM, Mattel released a special edition Ellen Ochoa Barbie doll in 2025 for Hispanic Heritage Month.
That kind of representation, it takes her accomplishments out of textbooks and puts them directly into the hands of young people. It celebrates not just her space flight, but her technical breakthroughs and her role in the entire STEM community.
So when we synthesize the entire arc of Dr. Ochoa's career, the enduring lesson is really the power of foundational specialized knowledge. Her entire career, exploration, crisis management, national policy, executive leadership, it was all informed by her intense specialized research into developing optical systems to help computers see and process information.
That esoteric skill, that niche expertise in complex information processing and defect detection, it directly translated into the operational excellence required to manage the most complex systems in space.
Right, to operate the robotic arm during ISS assembly missions.
And eventually to command the Johnson Space Center. Her transition from patented technical inventor to operational commander to CEO-level director, it provides a comprehensive template for applying specialized knowledge at scale.
She used the complexity of applied optics to master the complexity of command. She demonstrated that intellectual rigor in a niche field can be the catalyst for the most diverse and powerful leadership roles imaginable, spanning invention, exploration, and global strategy.
We hope this deep dive encourages you, the listener, to look at your own foundational skills and expertise. Dr. Ochoa's career trajectory from physics student to patent holder to astronaut, NSB vice chair, and now a board member of a cutting-edge tech company like NVIDIA, it shows that where you start is rarely where you end up.
But the depth of your knowledge is the engine that drives those unexpected transitions.
It's the fuel.
It is. We began this conversation with a scientist trying to teach computers how to recognize texture patterns and defects using applied optics decades ago. If that core technology has now moved from controlling rover robots in space to shaping the future of high-performance computing, a connection we can infer from her recent NVIDIA board appointment, this raises an important question for you to consider.
What's that?
What seemingly fundamental or niche scientific insight are you learning or mastering today that might launch the next completely unexpected and powerful phase of your career? That is the lasting and still evolving lesson of Ellen Ochoa's journey.
Welcome to The Debate. Today we're looking at the really extraordinary career of Dr. Ellen Ochoa, and it presents us with a fascinating paradox. We see this trajectory that spans groundbreaking science, space exploration, and eventually high-level institutional command. And it really forces us to ask, when does that technical brilliance yield to executive mastery as the defining legacy?
Exactly. So the central question that comes out of the source material is, well, was Ochoa's primary and most enduring contribution her pioneering research, her patents, her intellectual property, or was it her sustained high-level executive and operational leadership at NASA?
And I'll be arguing that her identity as an engineer and inventor is really the core of that contribution.
And I'll be taking the view that her institutional leadership is, in fact, the defining feature of her lasting impact. To have a career that starts with, such innovative research and then culminates in running the entire human spaceflight apparatus, it's almost unprecedented.
It really is. So let's delve into that initial identity. My position is that the foundation of Ochoa's lasting influence, it stems directly from her work in optical systems for information processing. We're talking about fundamental engineering achievement here. She was selected into the astronaut corps in 1990, not because of operational experience, but because of the raw excellence of her research that she'd already established at places like Sandia National Labs and the NASA Ames Research Center. And the evidence here is just crucial. She's an inventor. She holds 3 specific patents. And these aren't just, minor improvements. They represent durable intellectual property aimed at solving core technical problems. One patent, for instance, details an optical inspection system to detect tiny defects in repeating patterns. I mean, think about that practically. It's revolutionary for quality control in manufacturing things like semiconductors, the very components that enable our advanced space systems. Another patent involves recognizing texture patterns from photos, basically helping computers see autonomously. And NASA explicitly recognized this for potential use on the Mars rover. This role as a primary innovator, it really solidified her professional identity long before she ever sat in a cockpit.
Okay, and I come at it from a different angle. While those patents they're undoubtedly impressive, and they were the essential keys that opened the door to NASA, we have to look at the true scope of her influence. Her lasting contribution isn't the research paper, it's the large-scale systemic impact she had by translating that expertise into strategic operational control.
I see.
She didn't just fly once. She's a veteran of 4 space shuttle missions, STS-56, STS-66, and so on, logging nearly 1,000 hours in space. But it's the transition to institutional power that truly defines her. She rose quickly, becoming deputy director, and then on January 1st, 2013, she reached the absolute pinnacle of executive power as the first Latina and second female director of the Johnson Space Center. And she held that post for 11 years, steering the very core of American human space exploration. Her earlier roles, like deputy chief of the astronaut office, and especially as lead spacecraft communicator, Capcom, that critical link to the crew, that demonstrates a commitment to systemic oversight that just goes far, far beyond the singular brilliance of an individual patent. Her leadership shaped NASA for a decade.
That's a fair point on the depth of her administrative
tenure, but let's go back to the source of that authority. I mean, what made her qualified for those roles in the first place? We have to consider the basis of her expertise, her selection into that highly competitive 1990 astronaut class. It wasn't an operational hire. It was predicated on her prior research excellence. What's so striking to me is that she had this entire identity as a technical genius before she ever put on a flight suit.
Right.
Before she was even an astronaut, she was the chief of the Intelligent Systems Technology branch at Ames, supervising 35 engineers and scientists. She wasn't just at a lab bench, she was managing complex technical teams. And you see how her peers recognize this technical grounding, not her administrative skill, through very specific honors. She holds fellowships in Optica and the National Academy of Inventors. These are purely technical honors. Her position as a leader was secured by her technical prowess, which to me makes that technical foundation her most defining feature.
I see why you highlight those accolades, but, technical excellence is often a prerequisite for high achievement at NASA, not the achievement itself. Her technical background got her in the door, yes, but her executive tenure demanded so much more. It demanded the integration of that knowledge with vast operational experience. You can't run JSC by merely being an inventor. You have to have mastered the sheer complexity of the operational domain. Look at her missions. She was payload commander on STS-66, leading the science, and critically, her time in space included these huge operational milestones, like the STS-96 mission, which was the very first docking with the International Space Station. That required immense operational discipline, risk assessment, technical judgment, all in a high-pressure environment. That direct, high-stakes credibility is what earned her the trust to rise and to eventually succeed Michael Coates. Her influence only became truly systemic after she demonstrated that mastery of complex human spaceflight.
Mastering operations is certainly impressive, but that mastery is an application of her underlying intellect. I'm arguing about the durability of her contribution.
But let's look at the systemic influence. When Ochoa became JSE director, she wasn't just managing a branch, she was managing the core hub for all human spaceflight operations. Everything from astronaut training and mission control to ISS maintenance and preparing for the Orion program. This level of systemic influence, overseeing thousands of people, coordinating national policy, it arguably has a far greater long-term impact on NASA's direction than individual patents, no matter how important they are. The scope is just staggering.
Okay, but...
And furthermore, think about the operational weight she carried. Her presence was so profound that she was there in mission control during the Columbia disaster. That's not just an administrative seat. That is bearing the psychological and professional burden of catastrophic failure and managing the response at the highest level, making sure the organization moves forward. That's impact on a national, generational scale.
I acknowledge the massive responsibility of that role and the weight of being part of a disaster response. But administrative power, even held for 11 years, is tied to an organizational chart. It's tied to the current policy agenda. That role is by its nature temporal. The technology developed under her patents, those foundational optical systems, that is durable intellectual property. It continues to influence engineering fields regardless of who's in the director's chair. You can trace the lineage of visual inspection systems right back to her work. That technical idea, that concept is forever.
And what's more, her influence today confirms her identity as a technologist first. Her national service continues, not as an administrator, but as a technical policy shaper. She was vice chair of the National Science Board from 2018 to 2020, advising the President and Congress on science and engineering research. And right now, she chairs the Committee for the National Medal of Technology and Innovation. This continued influence over what technology the nation values, it comes directly from her roots as an inventor. She's advising the nation on technical merit, not organizational management.
That's a powerful distinction, I'll grant you that. But the influence she wields on the National Science Board or the Medal Committee comes precisely because she validated her technical foundation through massive executive service. She didn't just stay in the lab. She proved she could lead the most complex technical enterprise in the world.
We can also just look at the recognition from her professional peers. The fact that she's a fellow of the AAAS, the AIAA, and as I mentioned, the National Academy of Inventors. It all points to a recognition of substantive scientific contribution. While public honors like naming schools after her are incredibly important, of course they are, high academic recognition often favors the fundamental research that shifts paradigms, not just exceptional administrative execution. Her intellectual core is consistently validated by her scientific peers.
That's a compelling argument. But let's consider the breadth of her national awards that celebrate leadership and comprehensive service. We're sort of moving up the ladder of recognition here. She received the NASA Outstanding Leadership Medal in 1995 and the Distinguished Service Medal in 2015. These are agency-level honors for managing people and operations effectively, moving beyond technical design into strategic direction. And then, critically, she was awarded the Presidential Medal of Freedom in 2024. This is the highest civilian honor in the United States. It's given for contributions to the security or national interests of the country.
Right.
In the language of that award, it confirms that her legacy culminates in strategic, high-level executive and service roles that benefited the nation broadly far more than her specific doctoral research from the mid-'80s. The trajectory, as recognized by the White House, it moves from technical achievement to institutional mastery. And the highest accolades? Well, they recognize the latter, the comprehensive service that shaped NASA for a generation.
I appreciate the magnitude of the Medal of Freedom, but I would argue that her ability to achieve that institutional mastery, the very thing you're focusing on, is entirely dependent on the pioneering research she generated first. She wouldn't have been in a position to influence human spaceflight without first proving she could push the boundaries of technology itself. So, to summarize my position, Dr. Ochoa's career is extraordinary because she built it on the intellectual foundation of being a groundbreaking engineer. She advanced information processing with 3 patented optical systems. This fundamental technical intellect is the essential, durable engine of her entire professional identity.
And my argument stands that while those patents were essential, her true and lasting legacy is defined by her ability to translate that intellectual rigor into massive executive achievement. It's the difference between inventing a crucial part and running the entire factory. She didn't just fly in space 4 times. She became the leader of the Johnson Space Center for over a decade, managing the core of the U.S. human spaceflight enterprise through incredibly challenging times. Her sustained administrative direction shaped the trajectory of NASA operations, giving her a systemic influence that few inventors ever achieve, no matter how brilliant their individual IP is.
I think what the source material truly illustrates is just a rare career path, where foundational scientific achievement directly enabled organizational influence at the highest possible levels. It really forces us to appreciate that her career contains 2 full, distinct, world-class achievements.
Indeed. It forces us to consider where influence truly lies. Is it in the originality of a technical idea that lasts forever, or in the widespread strategic implementation of national policy and the sheer weight of directing the space effort for a decade? The material really demands that we hold both of those in high regard, and we'd encourage our listeners to explore her complete career path, from her work at Stanford to her tenure at JSC, to really determine for themselves where they believe the greatest impact truly resides.